Hello and welcome. In this video tutorial, we're going to be looking at Skills Practice 20.2, Standing Waves. Please remember to pause or rewind the video as needed. Let's begin. Read along with me, please. A wave that is a confined space is called a standing wave. Standing waves on vibrating strings of a guitar produce the sound you hear. Standing waves are also present inside the chamber of wind instruments. A string that contains a standing wave is an oscillator. Like an oscillator, it has natural frequencies. The lowest natural frequency is called the fundamental, or it is the first harmonic frequency. Okay? The other natural frequencies are called harmonics. There are two main parts of a standing wave. The nodes are the point of the string that do not move. The antinodes are the places where the strings have the greatest amplitude. You can see nodes and antinodes represented in the picture over to the right. In the picture over to the right, you're given the first 5 harmonics. First harmonic, second harmonic, third harmonic, fourth harmonic, fifth harmonic. Remember what we're given. Here we're given half a wave. Here we're given 1 full wave. The third harmonic we're given 1.5 waves, 1.5 waves. The fourth harmonic we're given 2 full waves. And the fifth harmonic we're given 2.5 waves. You can see that represented when we do this to the picture. This would be the full wave. You can see that harmonic number 1 is only half the wave. This would be the full wave for harmonic number 2. This would be the full wave for harmonic number 3. This would be the full wave for harmonic number 4. And this will be the full wave for harmonic number 5. You can see that the wavelength, which is that full wave, is getting smaller as the frequency of the harmonics is getting larger. Every 2 bumps, essentially every 2 antinodes, makes 1 wavelength. And we can find the wavelength by taking the length of the oscillator, length of the string, divided by the number of waves. Okay, and we're going to be using that as follows. Okay. Number 1, use the graphic below to answer these questions. A, which harmonic is shown in each of the strings below? B, label the nodes and antinodes on each of the standing waves below. C, how many wavelengths does each standing wave contain? And D, determine the wavelength of each standing wave. Let's do this. I'm going to make this a little bit smaller so you can see it. There we go. Okay, so I'm going to divide up the area. I'm going to do the work for wave A over here, wave C down here, B over here, and D over here. So I'm just going to split it up to show the different amounts of work that we need to answer those 4 questions. So which harmonic is shown in each one? Well, the harmonic number is given by the number of antinodes. So how many antinodes you see in the picture, that's the harmonic number. I see 1, two antinodes. So for A, we're looking at the second harmonic. Okay. For part B, for wave B, you're looking at the third harmonic. For wave C, you're looking at the first harmonic. And for wave D, you're looking at the fourth harmonic. Now, for each one, we want to label the nodes and antinodes on the standing wave. So let's do that. The nodes are right here where it's not moving. So we're going to label all the points that are not showing, all the points that are in between the antinodes. We're going to label it with the letter N to stand for node. You can notice that wave C does not have any antinodes because all you have is, or it does not have any nodes because all it has is one gigantic antinode. There's nothing in between. But waves A, B, and D all did. Okay, now I'm going to label AN to represent antinode. So one antinode here. Antinode, 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 antinode. Okay, and so for part B, we're labeling all the nodes and antinodes of these pictures. Okay, so that's part B. Part C, we're determining how many wavelengths we see. So how many waves do you notice? Well, for wave A, I see one wave. Okay, for wave C, I see a half a wave. For wave B, I see 1.5 waves. And for wave D, I see 2 complete waves. Okay, now let's make this a little bit more clear. Here's, I'm going to color code them so you guys can see. Here's one full wave. Here's 1.5. Here's only half. And here is 1 or 2 complete waves. Okay, so now finally, part D. Part D says determine the wavelength. Well, the wavelength, if you remember, is the length divided by the number of waves. So in the case of letter A, we're going to go 3 divided by 1 wave, and the wavelength will be 3 meters. For wave B, we're going to go 15 meters divided by 1.5 waves, and we'll get 10 meters for each wave. The wavelength for wave C is going to be 3 meters divided by half a wave. We only see half a wave, so the full wave must therefore be 6 meters long if you're only looking at half the wave. And finally, part D is going to be 15 meters. 15 meters divided by 2 complete waves. Or 7.5 meters. Part 2. Two students want to use a 12-meter long rope to create standing waves. This is very similar to our wave speed lab that we performed outside the classroom. They first measure the speed at which a single wave pulse moves from one end to the other rope, and they find that it moves with 36 meters per second. This information is used to determine the frequency at which they vibrate the rope to create each harmonic. Follow the steps below to calculate these frequencies. First, we're going to A, draw the standing wave for the first 6 harmonics. B, we're going to determine the wavelength for each harmonic. Okay, then we're going to fill the values in the table below. Part C, we're going to use the wave equation, speed equals frequency times wavelength, to calculate each frequency. D, we're going to acknowledge what happens to the frequency as the wavelength increases. And then we'll take a look at part E, in which case we're going to make a change to the length of the rope. Let's begin. Now, off to the left of the table, let's draw what these standing waves will look like. Okay. I'm going to draw, this is for number 1, first harmonic. I'm going to draw 2 points. Okay. And 2, 3, 4, 5, and 6. So for the first harmonic, I'm drawing 2 points. And I'm going to draw my standing wave by going from 1 point over to the right. Again, you're looking at half the wave. 0.5 wave. Okay, first harmonic, you're looking at half a wave. Now, for each trial, I'm going to make the 2 dots on the outside the same distance. But for the second trial, we're going to go and make another dot in the middle, and we're going to go up and down, and then complete the rest of the standing wave as follows. Number 3, we're going to create another dot 1/3 of the way and another dot 2/3 of the way, and we're going to go up, down to get the third harmonic. Each antinode should be fairly evenly spaced. To do the fourth harmonic, you're going to put a dot right in the middle. Then you're going to place 2 more dots between the black dots. You have a total of 5 dots evenly spaced. Go up, down, up, down, up. And there's our standing wave for the fourth harmonic. The fifth harmonic, we're going to go, now the fifth harmonic is the hardest one to draw. What we're going to do is we're going to go here, 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 and here. Okay, that's really hard to draw, but basically you're going to put 4 dots in the middle of the 2 black ones, fairly evenly spaced, as much as possible. And this would be your fifth harmonic. Okay, finally, the sixth one is pretty easy to draw. 1 dot in the middle. You're going to do 2 more dots over here and 2 more dots over there. Do that again. There we go. And you'll notice that the wavelength has gotten smaller as the frequency's gotten higher. Okay, how do we determine the wavelength? The wavelength is the length divided by the number of waves. Okay, so the length is going to be a 12-meter rope. So what we're going to do is we're going to go 12 meters divided by half a wave, and the first wavelength is 6 meters long. Oh, I'm sorry, that is not correct. Sorry, dividing by half is multiplying by 2, so the first one would be 24 meters. The second wave, the second harmonic is going to be 12 meters divided by 1, which would be 12 meters long. The third harmonic is going to be 12 meters divided by 1.5, which is about 8 meters long. The fourth harmonic is going to be 12 meters divided by 2, which would be 6 meters long. The fifth harmonic will be 12 meters divided by 2.5, which is 4.8 meters long. And then finally, 12 meters divided by 3 full waves, or 4 meters long. You can see as the frequency has gone up in the harmonic numbers, the wavelength has gone down. You can see that in the picture. And I'm going to draw that over here. Here's the wavelength of the first one, the second one, the third one, the fourth one, the fifth one, and the sixth one. And you can see the bright curve has gotten shorter and shorter. Finally, to find the frequency, we're going to go and use the wave speed equation. If speed equals frequency times wavelength, that means frequency equals speed divided by wavelength. So we're going to take this divided by this. Let's take the speed divided by the wavelength for each of these terms. 36 divided by 24 is 1.5 hertz. 36 divided by 12 is 3 hertz. 36 divided by 8 is 4.5 hertz. 36 divided by 6 is 6 hertz. 36 divided by 4.8 is 7.5 hertz. And finally, 36 divided by 4 is 9 hertz. Hopefully you see a pattern here that this is just 2 times the original frequency. If we take the original frequency, the fundamental frequency of the first harmonic, 1.5, and we multiply it by 2, we get 3 hertz, which is the second harmonic. If we multiply by 3, we get 4.5 hertz. If we multiply by 4, we get 6 hertz, and so on and so forth. If we multiply 1.5 times 5, we get 7.5 hertz, and 1.5 times 6, we get 9 hertz. Part D, what happens to the frequency as the wavelength increases? As the wavelength is increasing, and you can see the wavelength increases as you go in this direction here. So if wavelength increases, frequency is decreasing. Part E, suppose the students cut the rope in half. The speed of the wave on the rope depends only from the material the rope is made and its tension, so it will not change. Determine the wavelength and the frequency for each harmonic on a 6-meter rope. Well, what's going to change? Wavelength is the length of the rope divided by the number of waves. So we're looking at half a wave, 1 wave, 1.5 waves, 2, 2.5, 3 waves. So let's go 6 meters divided by half a wave, and we have a 12-meter long wavelength. 6 meters divided by 1 would be 6 meters. 6 meters divided by 1.5 would be 4. Okay, 6 meters divided by 2 would be 3. 6 meters divided by 2.5 would be 2.4. And finally, 6 meters divided by 3 would be 2. Again, you can see as the frequency is going up, the harmonics are going up, the wavelengths are getting shorter. You can find the frequency by going speed divided by wavelength. So 36 divided by 12 is what we'll start. 36 divided by 12 would be 3 hertz. 36 divided by 6 would be 6 hertz. 36 divided by 4 would be 9 hertz. 36 divided by 3 would be 12 hertz. 36 divided by 2.4 would be 15 hertz. 36 divided by 2 would be 18 hertz. You can see that each frequency is getting bigger by 3 hertz, meaning each frequency is a multiple of the original. All harmonics this time are now a multiple of 3 hertz. So as the length of the rope cut in half, the fundamental frequency and thus all the harmonic frequencies doubled.